Wow, this is a nice German translation. Okay. Yeah, I'm very happy to be here. Thanks a lot for the organizers to invite me here and make me give this talk. So yeah, I somehow was under the impression yesterday morning that this was going to be a 20-minute talk, and then I went with my family to the pool in Tübingen because we had 35 degrees, and I thought, okay, I better check, whether still is in order, everything is in order with the schedule. And then I realized it's actually a 40-minute talk. So and then I felt obliged to put some more information in, but I guess by now it seems that it would be better if I kept it to, let's say, a minimum. So let's see how we and whether we managed. All right. So yeah, before I start, just want to point out that, okay, Tübingen is here in the south of Germany, for those who are not familiar with it. So very nice medieval town, close to Stuttgart, pretty well connected. Actually, I flew out this morning from Stuttgart to London, so it's really easy to get here. And well, the group is growing. Maybe it's not as big as it is here on the photo anymore. But what I'm going to talk about here in the talk is mostly done by Matteo, who's finishing and actually joining Hannes. Yeah, so you should be happy and glad to have him in the group soon. And also Wayman and Markus Henrich actually have contributed to some of the results I'm going to present. Yes. The one here in the back. To the right? No, I think it's not. It's your eyes. A straight line down.
So maybe we keep urgent questions.
Yeah, I think the chair is getting nervous already. Physics here. So what I wanted to say also here, it's just to finish in the group is we are looking for postdocs, and actually this is kind of a nice situation we are in. So we are part of this so-called Henriette Herz scouting program of the Humboldt Foundation, and they basically give us some wildcard to scout Humboldt fellows. And well, if you are young, motivated, up and coming, eager to go to Germany and experience the research life there, and also get the perks from the Humboldt Society, please get in touch. Let's see, whether we can make this work. But I'm really encouraging, especially minorities, and also this includes, unfortunately, also females in Germany, to apply and have a good time in terms of science and also the life in Germany. So please, I strongly encourage you to pursue this. Okay, this is the overview of the talk. This whole talk is about kind of molecular processes and how to, let's say, emulate them, simulate them with Rydberg systems. It's really not my playing field, I have to say. And this is also the first time I'm giving this talk, but I think it's very appropriate that this is taking place in the chemistry building, because in spirit, I think it's close to what you would normally put into the box of chemistry rather than atomic physics, quantum simulation, and so on. So talk at the beginning about the basic idea, then of course go quickly to the Rydbergs. Talk a little bit about molecular dynamic processes in trapped ion systems, then in Rydberg tweezer arrays, linking to the title of the talk, and then do some summary. And then I thought I had to fill it another 20 minutes. So I put on the list some other stuff that I wanted to talk about, but maybe I just skip this in order to also make the chair a bit more relaxed. Okay, so molecular processes, why do we care? Well, it's a very personal view, I have to say. Why do I care? How do I motivate to myself why the stuff that we are proposing is in some sense interesting? Just what I want to state, so to say, is that understanding molecular processes that take place in the vicinity of intersecting energy potential surface, molecular surfaces, is somewhat important. And as I said, this is not my kind of main field of research, but when you look around at where these particular situations are encountered, crossing potential energy surfaces, then you quickly find that actually the process of vision somehow is related to that. And just to talk you through the plots, it's just sufficient to look at the left because the right hand plot is the same. So you have here some kind of energy, on the y-axis. You have here some effective coordinate, it's the so-called isomerization coordinate. And then you see these potential surfaces here that you can calculate with some theoretical chemistry understanding. And then what you see is that, well, of course, you can now, since these are potential energy surfaces, you can create wave packets, you can promote them to some excited state, and then they will evolve under certain dynamics, and then they will encounter occasionally these crossings, and they may tunnel through those or come back and oscillate and so on and so forth. But why am I showing this particular example? Apparently, vision works in a way that your photoreceptor absorbs a photon, and then you create an excited state of some complex here that then can undergo an isomerization transition, so it becomes a different isomer when going through this crossing here, and this isomer then can stimulate this optical nerve, and apparently then you see. So, and you see this has been under investigation already for more than 30 years, and also more recently is gotten into the focus again. Here's actually a result of numerical simulations compared to experiments here. And I mean, if you look around, I mean, you find all sorts of situations where these kind of dynamical processes are actually studied. Problem is somehow that everything is, kind of hidden at very small length scales. Typical length scales here are angstroms, and the processes are taking place in very fast timescales, picoseconds, femtoseconds. Numerical simulations are challenging. I mean, okay, my understanding, everything is not always that nice. I mean, you see this is a very complex molecule, and you basically boil everything down to a one-dimensional description in terms of 1 degree of freedom. So typically the situation is more complicated. You have many degrees of freedom. You have non-adiabatic effects. I will talk about this near this intersecting curve. And typically you have this high dimensional configurations. Just a more recent example linking to something different, not the process of vision, but something that goes under the name intercoulombic decay, which happens when you bring two atoms close together, and then you pick out with a high intensity light pulse one of these inner electrons of one atom. And what then happens is that this hole that you create here, that you leave behind, that can be filled by another electron that releases energy, and this can actually then ionize a nearby atom. And I just show you the results, a plot taken from this paper where this is investigated in a system of argon atoms or ions. And what you see is that you basically have a trans or a process basically which leads, which creates from this whole state, this ionized atom, another highly excited atom here, which then also basically spontaneously ionizes. Long story short, what you see now, is here as a function of some time delay in some probing scheme. Doesn't really matter what the details are. What you see here are modulations, that you find in the system, and actually these modulations, you will see now what I'm aiming at, come about due to the fact that this wave packet that you excite now in this molecule undergoes some complicated dynamics, which is related to this motion inside this potential landscape where potential energy surfaces intersect. And then you see here, I don't know, I think you can follow this like a movie from the top to the bottom. You excite here in this landscape a wave packet, and this wave packet then can propagate, and then it gets reflected back from this wall. And then you see there are several branches, several crossings. It's where it has to decide which way to go, and you can imagine that with each crossing and each reflection, the number of channels increases, and you can have these interference effects in the end, which give rise to this modulation. So this is just an idea of what sort of complicated stuff can happen here. And now the question, that's why I guess we're all here. Wouldn't it be nice to see something like this more directly in Rydberg systems? This is somehow the question of the talk. So, of course, the connection between Rydberg atoms and molecules is also not new. I mean, there are a number of people in the audience who have pioneered research in this field. There's, of course, this vast field of ultra-long-range Rydberg molecules, which come, and Rydberg macrodimers, whose difference is that in one case, you have a ground state atom inside the wave function of the Rydberg atom, and in the other case, in this microdimer case, you have two Rydberg atoms that have funny shaped potential surfaces that end up in the end with some kind of attracting well, and you can get bound states between two atoms that are excited simultaneously to the Rydberg state. And then there's another kind of direction, that is pretty related. It's the direction of Rydberg aggregates. Here, the idea is that you basically excite Rydberg states at different positions in space, and then you have dipolar interactions between these Rydbergs. And something interesting then is happening as a consequence of, I don't know, electrostatic interaction between the Rydbergs, concomitant exchange interaction, and also coupling to the external dynamics. So this is more the idea that I would like to build on, in this talk. It brings us to these artificial molecules that I want to advertise. So the idea here would be to use Rydberg states, of species that are confined in an external potential, and these species form somehow objects, that have electronic degrees of freedom and vibrational degrees of freedom, but unlike, let's say, normal molecules, that's why I call them the artificial molecules, these objects do not have to be necessarily self-bound. So they can also just be confined in an external trap, so that things don't fly apart. But at the end of the day, you have still electronic degrees of freedom, you have vibrational degrees of freedom, and this is, so to say, what I would say, from my perspective, makes up molecular dynamics, and you have a rich playing field in which you can explore hopefully interesting things. So one project that started some time ago with Markus Henrich and Byron Lee explores this idea in systems of trapped Rydberg ions. And you know, when you have ions that are positively charged, when you bring them close together, they repel each other. You confine the ions, then there's a balance between the repelling force and between the ions and the confining potential. And then when the temperatures are sufficiently small, you find that you get in the end such a Wigner crystal, where the ions sit at their equilibrium positions, but also vibrate around the equilibrium position. So you have these vibrational degrees of freedom. So what you now can do is you can combine this with Rydberg excitations. So again, I mean, although you have positively charged objects, of course, these ions also have Rydberg states. So you can excite the electrons or the valence electrons to high-lying orbits. And then you have all the nice features that you also have for neutral Rydberg systems, with some complications and also some advantages, but this will probably be too much to be talked about in its entirety here. But at the end of the day, what you have is you have now vibrational degrees of freedom, you have electronic degrees of freedom, and the combination of this also gives you potential energy surfaces along which or within which, for instance, these ions are vibrating. And if you tailor your system in a way that makes stuff interesting, you can even achieve a situation where you have in the Rydberg states, in the ionic Rydberg states, potential energy surfaces where you find such kind of intersections that I showed you at the very beginning. So this is kind of the basic story of showing you the direction of travel in this talk. The nice thing, however, is here that everything is kind of blown up in comparison to actual molecules. So we have slowest time scales in comparison to the picoseconds and femtoseconds. So we have here microseconds, and the length scales this is factor 10 or 10,000 even larger. So from nanometers to micrometers, compared to traditional molecules. Then just to show you what one could actually explore there, that one could deem interesting, I pick up something that we have investigated in this paper, where we look at trapped Rydberg ions and intersecting potential energy surfaces that we can create by exploiting Rydberg excitations. So the bottom line is, I think, very quickly explained. So look at this plot here. So this is the energy, and this is some coordinate, and this is some other coordinate. So the two-dimensional space. And you see here that when you now calculate these potential energy surfaces, you use the Born-Oppenheimer approximation typically, so you diagonalize the electronic problem using the nuclear coordinates as parameters, and then you plot the electronic energies as the function of the nuclear coordinates, and then you get these kind of surfaces. And how we did it doesn't matter at this point. So this situation is such that we get here this nice intersection. Yeah, but you see there's some kind of double well here. So there's a minimum here, and there's a minimum there. Yeah, this is now what's plotted here. Yeah, down here. So this is also the double well. These are the iso energy lines. So this is the left double well, and this is the right double well. And now if you take this potential, you place a wave packet in the left double well, and you let the system evolve. Well, what will happen is that this wave packet tunnels to the other side, and then also comes back. Yeah, you see this here. Here's the population of the two wells. You see these nice, they're not harmonic, but you see the nice oscillations of this wave packet, which is tunneling back and forth. This is what you get when you sort of say naively, in quotes, yeah, calculate these Born-Oppenheimer surfaces and take them seriously as a potential within which you can evolve your molecular wave packet. When you actually do the calculation without this adiabatic Born-Oppenheimer approach, what you find is that the real dynamics in quotes is not like this. Yeah? So in reality, if you plant here a wave, prepare here a wave packet in this well, nothing's happening. Yeah, so you see there are some oscillations within this well, but if you wait and wait and wait, so there's no tunneling from the left well to the right well. So you just stay stuck. And the reason for this is that in the vicinity of these follicle intersections, you can actually pick up geometric phases. Yeah? And in this case, it happens that there is a phase that you pick up when you go, let's say, around this touching point here along the left-hand side or along the right-hand side. So you pick up a phase every time, but the point is that these phases are exactly opposite, and you get destructive interference on the other side. So you see there's this non-adiabatic effect that is very prominent in the vicinity of this intersection that completely makes the results contradict the naive expectation. Oh, and I hope you are convinced again that this is something worthwhile studying. Yeah, of course, the situation can become easily far more complicated. Yeah, so this is a situation of two ions. Yeah, imagine now much more complex systems. Yeah, 5 ions, 6 ions, 10 ions, 100 ions. Yeah, so the number of degrees of freedom blows up dramatically. So this is not something that you can easily simulate on a computer. This is also why the theoretical chemists have work to do. Yeah. Okay, so now let's move away from this already published work to, let's say, something new. And here we are looking at similar physics, but not taking place in trapped ion systems, but in Rydberg tweezer arrays. So I don't think I have to talk about Rydberg tweezer arrays. I'm sure there will be many. There have been already plenty of talks about those. Here's just the sketch from the theorist side. So what we consider here is a triangular set up, yeah, where we have 3 traps here placed on an equilateral triangle, and we neglect the dynamics out of the plane. We just say it's frozen, and it's anyway just a spectator for everything, and we only look, so to say, at the 2-dimensional motion in plane. Yeah, and then you see that for each of these tweezer arrays, we can now tweezer traps. We can make now an harmonic approximation, and we get 1 phonon degree of freedom for the vibrations in the x direction, 1 phonon degree of freedom for the vibration into y direction for each trap. Yeah, so these are 6 phonons here. Now we have the electronic dynamics. I don't know whether anyone talked about facilitation. Yeah, but what we will do here is we look at Rydberg systems where we model our Rydberg atom as usual with the electronic ground state and the Rydberg state. And now we excite Rydberg atoms or Rydberg states in a way that the laser detuning just cancels the interaction energy when 2 atoms are at this position at the interparticle distance d. So this is the facilitation condition. Why is it called facilitation? Because simply when there is 1 atom already in the Rydberg state, then the excitation of the neighbor is actually resonant and then proceeds as a pathway. So now why am I doing this? Yeah, I'm also doing this to simplify the problem a little bit. Because it turns out, for this 3-side setup, the energy level structure becomes really easy. So you have 2 states which are split away, yeah, so that are kind of spectators. This is the state where all atoms are in the Rydberg state and all atoms are in the ground state. And all the other states, the other 6 states, they're actually resonant, because they're always they're coupled, so to say, by a facilitated spin flip. When you see they form something like a tight binding model, here with 6 sides, where the hopping rate between these states, which are labeled 1, 2, 3, up to 6, is given by the Rabi frequency of the laser. So what we have is 6 phonons, 6 electronic states. So now, interesting stuff happens when we couple this. So how are the phonons coupled with the electronic degrees of freedom? Well, this is the sketch that hopefully says it all. Sorry, slight change of notation. I copied this in this morning, but because I thought it's probably the easiest way to understand it. When you excite, these are now the pair states of the two atom setup. So 2 atoms here in the ground state, 1 atom in the Rydberg state, and 2 atoms in the Rydberg state. And now when 2 atoms are in the Rydberg state, they of course interact. So there's an energy shift. But of course, this energy shift is also spatial dependent. So this automatically leads to a force, right? If you have an energy that depends on position, then you have a force. And what you find is that when you excite 2 Rydberg states, then these wave packets, 2 atoms to a Rydberg state simultaneously, then their wave packets get kicked by this repelling force. In this case, could also be attractive, doesn't matter. So this is the mechanism that couples the electronic and the phononic degrees of freedom, and the coupling constant is just given by the gradient of the interaction potential. Evaluated at interparticle distance. So, and with some harmonic oscillator length related to the confinement strength of the atoms in the tweezers. So then you can write down the Hamiltonian. This is nice. I mean, for theorists, I mean, you can write down something that looks not completely ugly. So we have here your 6 vibrations. You have here your electronic dynamics, which is basically governed by this tight binding model with 6 sides. And then you have here this Vibronic coupling, which is just a result of this first order expansion of the interaction potential around the equilibrium position. And these constants D here are just geometric factors, depends on how you couple to which mode when you happen to excite a certain state. And the overall coupling strength is this kappa, which is just the gradient. Okay, so now you can calculate your, it's in quotes, molecular spectra. So basically you take this Hamiltonian, you calculate the spectrum, and you try to understand. So, and I show you now here 3 spectra, and from the left to the right, we increase the Vibronic coupling strength. So this kappa. So at first, this kappa is 0. So, and what we just get here are tight binding models, so tight binding energies. You can diagonalize this tight binding model very easily. You just get a linear increase of the energies with omega. And you see you have many of these models, because they are all separated by 1 or more trap frequencies. There's an infinite series. Okay, the pointer doesn't go beyond the screen. There's an infinite series of these states, because it's just repeated in units of the trap frequency. Now you turn on this coupling. And so the coupling between the vibrations and the electrons, and then you see that these degeneracies here that you found here are actually slightly lifted. So there's some coupling now between these states that I showed you here that are kind of hybridizing. These couplings hybridize the electronic and the phononic degrees of freedom. And you see this even better in this regime here, where the coupling is relatively strong. You see here there's one regime, which is dominated by this Vibronic coupling. You can also calculate the energy. I mean, I just show this, because it's actually conceptually super easy to calculate this, but solving the integrals and the sums is actually Matteo did all this, it's not super straightforward, but it can be done, and then you can compare this with a numerical exact result, and you understand this very well. And I show you also this because later on we get also analytic expressions for the actual hybridized state, that lends to itself to a nice interpretation. And then for the largest, for larger omega here, what you will eventually get dominated again by this tight binding physics. So we get again this kind of straight line in the end, if you look at the ground state. So there are 2 regimes here. So there's one regime, I call this now JT, so Jahn-Teller, I explain in a second why, and then there's this kind of normal regime, which is not so spectacular because it's just all dominated by the electronic dynamics. Okay, so now, how can we now understand a little bit better what is happening in this regime and why actually this connection to Jahn-Teller? Sorry for the misspelled here. So what we can do now is we can look, take a slightly closer look at the state that this combined electron phonon system assumes here in the regime where this coupling, the Vibronic coupling, is dominant. So we can write down the state, and this looks like this. So the state is composed of 3 components. And actually, let's just understand this first one, and then the other 2, they are easy. Yeah. So you see, this is a superposition of 3 states, and each of these states is a product state of, so to say, an electronic component. So this 1, you see, this just happens to be this state. I mean, of course, it's completely arbitrary how I label this, but so just for the sake of concreteness here, this is this state. And when this system is in this state, then the phonons, the 6 phonons, are in that state. Yeah. So again, think of our triangle here. So trap 1, trap 2, trap 3. So this is the displacement of the so to say trap state, yeah, in x direction. So displacement, this is displacement of trap 1. This is a displacement of trap 2. If I draw this now, it's maybe easier to see. You see that this is actually becoming a distorted triangle here. So all the other traps, or the other phonons are in the ground state. The only 2 modes or two phonon modes that are displaced from the ground state are the x modes corresponding to trap 1 and trap 2, and they are just displaced in the opposite direction. And this is exactly the Jahn-Teller effect. Yeah. So where you see that in each of these 3 components, yeah, you have now actually a distorted triangle. If you look at the quantum state as a complete object, yeah, no problem. If you look at this quantum state as a complete object, is of course this triangular symmetry. But each of these components doesn't obey this triangular symmetry. It has a lower symmetry, and this is the essence of the Jahn-Teller effect. You see this even better if you think about now these Born-Oppenheimer surfaces. Yeah, if you calculate now the Born-Oppenheimer energies, and you also have to, in order to make this, to be able to visualize this, you have to play a little bit with the system and find out what are the actually relevant modes. Yeah, I mean, 6-dimensional space is a bit difficult, but it gives me 3-dimensional space you can plot, and it turns out that only 3 modes, 3 collective phonon modes, play a role in this system. All the others do not couple and are just spectators. And if you find out which mode that are, you can now plot the energy surfaces as a function of these collective coordinates, Q1, Q2, Q3. And what you find now is that in this Jahn-Teller regime, where the ground state looks like this, I get just 3 degenerate minima. Yeah, so in these bubbles, each bubble shows an ISO energy surface, and the darker the green, the lower, the smaller the energy. You see, these are really 3 degenerate minima. And of course, now quantum mechanics, yeah, says, okay, the ground state is assumed by the superposition of the 3 possibilities. But in practice, any small symmetry breaking field will make you collapse to one of these minima. Yeah? And this is what you see, so to say, as a consequence of the Jahn-Teller effect. One of these distorted triangles will then be selected. And you see that actually the ground state of your triangular system is not an equilateral triangle. Yeah? This is how it's supposed to go. So, and then you can now look at, I told you already that this is going to be boring. Actually, nevertheless, what's happening? You can look at the regime in which you crank up this Rabi frequency, and you basically increase the importance of this tight binding dynamics over the electron phonon coupling dynamics. And then you see, as you move along, yeah, these 3 minima collapse, yeah, and you just get a state which is just 1 minimum. Yeah, this is completely symmetric. Yeah, this obeys then this triangular symmetry. But okay, if you look at the state, it's completely boring. It's just the phonons are in the ground state, and for the electronic state, you get just a can call it a spin wave. Yeah, this momentum pi. It's just a product state, and there's nothing interesting happening. Yeah, so there's also then no entanglement here between the phonons and the electronic degrees of freedom. Okay, so this brings me already to the summary, and I think I will leave it with that. So I hope I could give you an idea of, well, our idea to look at molecular processes, yeah, in these Rydberg systems, be it systems realized with tweezer arrays or Rydberg ions, doesn't matter. So, I mean, I think it's in general something that is interesting to pursue. It's getting complex very, very quickly. Again, I showed you here the simplest manifestation, I would say, of something interesting. You can imagine if you now, as soon as you include more atoms, I mean, the complexity of this whole thing explodes. What you can also do is actually quite interesting. There are certain regimes in which you can integrate out the phonons, and then you get an effective non-binary interaction between the Rydberg atoms, which is also related to the fact that they experience forces that are actually state dependent. And I think I want to leave it with that. I would have thought that I could manage to talk about other works that are going on in our group. One is in quantum reaction diffusion dynamics. The other one is on machine learning dynamical generators of open quantum systems. But I think in the interest of time and also for having a closed story, there's no point in just digressing now. Thank you very much.
Well, thank you very much for showing us what one can do with these systems. This is now open for discussion. The questions. We start here, right, and then afterwards, Rosario.
I have just a very quick question. Did you actually plug in some experimentally manipulated numbers to see if you can get it?
Yeah, we can talk about this. Yeah, I mean, you get displacements on the order of tens of nanometers, let's say, and I mean, in Stuttgart, yeah, with this ion microscopy, so field ionization, at least it was possible to observe displacements of that order. So I'm quite optimistic that this works, but probably there are also other ways to probe this. Yeah, so let's discuss. Yeah.
So Rosario?
How do you include the non-adiabatic effect when you see the localization of the
full numerics? Yeah, well, it's a pain, but I mean, you can do it for the two ions. If you throw away all modes that you think have nothing to do with the dynamics, but of course, it's also some brutal approximations that you have to do there.
Yes, please.
Can you comment on how tunable these many-body spin interactions are?
I'd love to comment on this. They're actually depending on the lattice geometry. I mean, okay, maybe this is the way to understand this. Yeah. So if you, I don't know how familiar you are with phonon-mediated interactions in ion traps. It's exactly the same idea. Yeah. So in ion traps, you do this create such interactions by kicking the ions, yeah, in a state-dependent way. And when you integrate out the phonons, yeah, you see that this state-dependent kicking, yeah, actually gives rise to a sigma z interaction, yeah, because somehow the sigma z encodes the state dependence of the force, whether it goes to the left or to the right, depending on the state. And how this looks is actually strongly dependent on the lattice geometry, yeah, because I mean you have to understand which mode feels which force, and then also depends on what energy does the mode have, yeah? So because this somehow gives its relative weighting to others in this second order expansion that you for the energy shift that you have to compute in order to get this effective interaction. This is not a very well-defined answer, but it's tunable. Yeah.
The problem that you were discussing is called the E cross E Jahn-Teller effect. Yes, so because you have an E electronic degeneracy, and it's the E modes that are Jahn-Teller. So this problem has been studied in lithium-3 by Wolfgang Dehler in Kaiserslautern. And what you find in the regime when you have the 3 minima is the pseudo rotation. Okay. So the main motion, nuclear motion, pseudo rotation that is subject to the geometric phase that you mentioned earlier in the video. No. So I don't know whether you looked at that because that's the real use in the problem.
I mean the lithium-3 I found, yeah, but okay, not.
So the pseudo rotation phase because your 3 atoms are turning in phase. And the total motion is actually subject to the geometry phase because you treat the problem in the lower adiabatic sheet. So you should look at it.
Yeah, I will.
Probably you can find this.
Yeah.
In
I mean, here it's a bit of a special situation because, as I said, okay, I will definitely look at this. I mean, this is exactly what I was hoping to get out of this talk. Yeah. Here, it's a bit different to the standard problem because there's not this. These are not self-bound molecules. You always have this external confinement. And so to say, at the kind of technical level, this enters because you couple to one more mode, to one more vibrational mode, and then one has to check whether this spoils this effect or not. Because for the kind of self-bound equilateral triangle molecule, lithium-3, you only couple it to two of those modes and not to the third one. So maybe there's a difference. Okay. Well, let's just see. Thank you for this comment. Yeah.
So I see no further questions. Let's thank our speaker.
Thank you.
And the last